We're talking about wave functions today, and we'll be dealing with wave functions for the rest of the semester. So it's pretty important. We want to make sure we have a pretty good idea of how the state vector and the wave function are related. So far we've been dealing with this state vector. We've been dealing with spin, so here we can write any state vector in terms of two eigenvectors. And in this case we did it for the z, and so it's either aligned with z or anti-aligned with z. Now with position, we're going to find we have very many more options, right? In fact, infinitely many in general. But we can still treat it the same way. We can make little bins, okay, and say bin 1 is position x1, bin 2 is position x2, and we can treat these things just as we treated the eigenvectors from before. And so now we get, this is kind of a tricky look at little picture, but basically the idea here is that we have some vector that has an infinitely many components. And so the wave function is going to be a representation of a state vector with infinitely many components. And so we want to see how that works. Now position is continuous, right? Where spin projection was quantized or discrete. And so we'll find in quantum mechanics some things are discrete, some things are continuous. And so we've dealt with the discrete case, and so now we want to look at the continuous case a little bit. And so one way we can do this is for position, for instance. Let's just say our particle is going to be somewhere along here. And so what we want to do is we want to break this into little bins, okay, that have length delta x, and so we'll name them. So this will be like x1, x2, x3. Now suppose I keep doing this, and then at some point we'll get into some regions where this will be like the x to the ith point. This is the x minus 1 point, and this is the xi plus 1. And so we can actually represent this here. And so again, these if I'm in the eigenfunction xi, that means my particle is in this bin right here. Okay, this is the bin x2, then here's just, you can imagine this is filled with bins through here, and this is just the ith bin and whatever. And again, the thickness of each one of these bins is delta x. So the thinner you make these, the more accurate they are. Okay, now you can go through and do your system like this, and it'll be fine. But we're going to find that the wave function is a nice alternative to this, because right now you have this infinitely long vector, which is kind of difficult to deal with. So just to go along with this same picture, so here's our state vector, and so what we can do to make this easy is we can make these eigenvectors pretty simple. So here I just picked 3, and basically these eigenvectors are infinitely many zeros in theory, with just one somewhere to represent that particular one. So here's the ith one has a 1 right there, the I to the minus 1 has a 1 right there, and this one has a 1 over here, and then the idea is that there's 0 everywhere else. And so just with this picture here, I want you to think about this inner product of xi and x to the I plus 1. So go ahead and pause and think about this. What does that come out to be? And we'll talk about it. All right, so I got 0. And so again, what this works out is it depends on what, if you look at here, just two different vectors. Now we know that basically these are going to have 1s at different points. And so in this total case here, if I take the inner product of these two, you're going to have 0 times 1 and 0 times 1, and it should be equal to 0. Another way to sort of phrase that is that these should be orthogonal. All right, these vectors. Again, it's sort of the idea that if this is the probability that if I'm in the x to the I plus 1 state, I'll be measured to be in the xi state, and that should come out to be 0 no matter what. So our general state vector is going to have a look kind of like this here. Okay, so it's going to be, you can write it as a column vector. Here's our state vector, and you've got these little things here we call the psi sub i's. Okay, so the psi sub i's here. And basically this psi sub I is just going to be an inner product of that particular, the ith x eigenvector with the general state vector. And so this thing is going to be a quantum amplitude, right? So this is the quantum amplitude that I'm in the x minus 1 bin, is what that comes out to be. And so if we just do a little bit more machinery here, we see that basically your vector, you can write it either as the column vector as we've done, or you can even write it here as a sum of these guys here, where these coefficients, we've been calling these the c's, but now with the wave function, we're going to call these psi sub 1, psi sub 2. And that's, again, a quantum amplitude, such that if we square that, then what that comes out to be is the probability that you'll find your particle in that particular bin. All right. Now, this is a fine way to do it, and if you do it this way, there's a direct analogy to the state vector. I mean, this is a state vector. This works exactly like the state vector. The only problem is you have an infinite number of these, and it just becomes very difficult to use this. And so we have a nice sort of picture like this. That we're basically, these are little quantum amplitudes, which we were calling our psi's. This is like the psi 1, and so we can represent all these quantum amplitudes here. And again, if I take the absolute square of these, that gives us the probability to find our particle in that particular bin. And you can just sort of hopefully see that, well, another way to kind of think about this is to just write this as a nice continuous function. All right, and this nice continuous function is our wave function. And so it's very similar to the state vector. All right, there's going to be a lot of analogies with the state vector we're going to talk about, but it is a different thing. And so we want to talk a little bit about those differences. So to me, the biggest differences between the wave function and our state vector can be seen here in this clicker question. So we're asking, what are the units of the wave function? So we're going to shift our interest to this thing, the wave function, psi of x. And maybe you've seen in the texts, this is how we're going to define normalization. All right, so if something is normalized, we can say that the wave function squared, the integral over all space dx is equal to 1. Well, in order for this to be true, what are the units of the wave function? So give this some thought, and we'll talk about it. Okay, so hopefully you got this one here. This is definitely tricky. So when we're doing this integral, all right, over here, we want this to be unitless. This is a probability, so we want to have no units over here. And so when we do an integral, there's a dx, right, as length, so it's going to have units of meters, which means the psi squared should have units of 1 over meter, right? So that these 2 meters cancel and we get unitless. And so if we just real quickly sort of look at this, so if psi squared has units of 1 over meter, then if we take the square root of both sides, we're going to have 1 over the square root of a meter. So that's the answer for this. And you can think about this by, say, going back to first year and thinking about something like, for instance, the linear mass density. So when you talked about a string, you usually talked about the linear mass density, and that was a mass per meter. And so if you want to define, say, the mass of a particular segment, so here they're saying, let's try to find the mass of this segment that's delta x length, and it's at this position x. What you do is you take the linear mass density, mu of x, times delta x. And of course, what the units of this was, it was kilograms per meter, and then your delta x would be in a meter, so this would cancel, and you'd be left with your mass in kilograms. Well, it's the same idea here, right? You can't really talk about the probability at a certain infinitesimally small point, and so what we do is you talk about the probability density at that point, all right? So with the probability per unit length. Now, of course, the thing that's tricky here is when we talk about our probability density, that's going to be our absolute square of psi. All right, but you can still talk about that. That will be units of probability, which of course is unitless, divided by meters. And so if you want to find the probability, say, in some little region, so here's a little region, delta x, what you'd do is you'd find your probability density and then multiply by x. All right, and so again, that's units of probability over meters times meters equals units of probability. And so when we're all done with this, what we'll be able to do then is define this here. And so what we'll do oftentimes, we'll say, okay, so what's the probability to find our particle in some region? And so here's just some wave function, psi of x, that we just made up, and say here's 2 points, psi 0, psi of I. I want to find the probability to find the particle within that region, define this here. And so you take the wave function squared, which again, this gives us our probability density, and then integrate over dx between that region, and that'll give you the total probability, unitless, of finding the particle in that region. And so just to kind of summarize, discrete versus continuous. And so the state vector and the wave function, again, they're not the same thing, but they're similar and they carry very similar information. So in the discrete case, right, we would write our state vector, something like this here. And so some linear combination of two state vectors with these little coefficients out front. And then the continuous, now we're going to have a wave function. So here's an example of the kind of wave function we'll start using in a week or so. And you can plot this. And so this is the wave function right here. All right, and this carries information about probabilities of different experimental results for this particular object, just like the state vector does. And so it's the same sort of thing. It sort of carries information about certain probabilities. And so for the discrete case, we know that, for instance, if I take the absolute square of C of A, that was the probability my quanton will be measured to be in my state A. Well, for this particular, and then of course we know that CA squared plus CB squared equals 1, and that was the idea that it was normalized, okay, that it's basically 100% probability that you'll get one of the results. And so now this is our probability density, psi squared. All right, and what it tells us, and so here's a little plot of it, is it basically gives us information about where it's more likely to find your particle. So for this particular case, the most likely point to find our particle will be right here in the middle. So we're talking about some region from, say, 0 to L, and I think it's 0 on either side of those. And so this would be the most likely spot to find it, and you're not very likely to find it at 0 or L. So we can get information here about our position, okay, which is what we're moving to with the wave function. And then our normalization is that if you integrate this probability density over all space, you should get 1.